and welcome to this video workshop presented by Macnica Americas. This presentation will acquaint you with Bluetooth SMART concepts. I'm Troy Jones, a member of the technical staff here at Macnica Americas, and I will be leading you through some of the details of Bluetooth SMART. This will include becoming familiar with Bluetooth SMART basics and the technology fundamentals. I will touch on the rudimentary ideas behind Bluetooth SMART low power, and then dive into the protocol stack. From there, I will discuss some Broadcom specific devices to enable Bluetooth SMART on your next project, and then I'll introduce you to the Mpression Odyssey Bluetooth SMART sensor development kit. Let's start by taking a look at some Bluetooth SMART basics. Sometimes you may hear the term Bluetooth Low Energy, or BLE. This is the same thing as Bluetooth SMART, and it is not Bluetooth Basic Rate or Bluetooth Enhanced Data Rate. BLE is a different technology from its predecessors. BLE was designed with 3 constraints in place, along with 3 additional goals above and beyond those of standard Bluetooth. It had to reuse as much of the Bluetooth RF as possible. It had to reuse as much of the L2 CAP protocol as possible. And the host controller interface had to be maintained as much as possible as well. The 3 goals that needed to be achieved were to use as little power as possible, have the lowest latency possible, and to create a very wide interoperability infrastructure. With those constraints and goals in mind, the Bluetooth SIG defined Bluetooth Low Energy in version 4.0 of the Bluetooth spec, specifically adding volume 6. As you evaluate the capabilities of BLE and how you can leverage the technology in your next system, keep in mind that it was not designed for high data rate transfers or extended range. It was, however, designed to be very small, low cost, robust, low power, and the best of all, license and royalty free. As mentioned before, BLE leveraged many Bluetooth specifications, but was allowed to incorporate changes to adhere to the constraints and achieve the goals placed on it. Here we can see some of the low-level details that Bluetooth SMART employs. It operates in the 2.4 GHz ISM band with a theoretical maximum data rate of 1 megabit per second. But in reality, you'll see rates around 300 kilobits per second. The specified range has a maximum of somewhere around 100 meters, but again, in true application, you'll probably get closer to 50 meters. Security is achieved by using 128-bit AES encryption, along with additional layers of security that can be defined in the application. Furthermore, BLE uses a star topology and frequency hopping between the central, which is the master, and the peripheral, or the slave, with a 24-bit CRC to create very reliable connections. The BLE specification calls for a transmit power of something between 10 microwatts and 10 milliwatts. Speaking of power, what does Bluetooth SMART mean when it claims to be low power? First off, the physical silicon required to create the BLE radio is only about 60% that of a standard basic rate or enhanced data rate Bluetooth device. And since Bluetooth SMART is designed for infrequent small data packets, that radio can be off most of the time. BLE peripherals advertise on only 3 channels, and the protocol is optimized in such a fashion that a connection can be made and minimal data sent within 3 milliseconds. The spec allows for relaxed RF parameters and increased modulation indexes as well. Because of all these energy-saving features, Bluetooth SMART is ideally suited for applications that can run off a coin cell battery. Next, let's dig into some details of what makes Bluetooth SMART Bluetooth SMART. As with many modern-day communication and data transfer systems, there is a protocol stack that defines how information is handled between different layers. The Bluetooth LE stack is similar to a Bluetooth stack, but is different by definition. I will not be comparing the 2 stacks here, but instead we'll discuss each layer of the BLE stack from the lowest layer, the physical layer, up through the highest layer, the applications. Let's start with the physical and link layers first. Recall that BLE operates in the ISM band around 2.4 GHz and has a theoretical bandwidth of 1 megabit per second using GFSK modulation. There are 40 channels on 2 MHz spacings on which BLE communicates. Within these 40 channels, 3 of them are reserved purely for advertising, while the remaining 37 channels are used to transfer data. You've heard me mention a few different terms for BLE devices, such as a master or a slave, or a peripheral and a central. So, what are these things? Well, they are roles a device can assume as defined by the spec. As you can see here, there are 4 main roles a device can take on. Keep in mind, a device can support multiple roles simultaneously. So, a broadcaster, at a minimum, will send out advertising events, meaning he is blindly shooting out packets just hoping someone is out there listening. The counterpart to a broadcaster is an observer, in that, at a minimum, it listens for advertising events. Now, beyond simply sending or receiving blindly, the roles of the peripheral and central are defined. A peripheral, also defined as the slave, will both send and receive packets and will accept an invitation to establish a connection, whereas the central, or master, will be the one to initiate a connection, and it too has both transmit and receive capabilities. The next layer above the physical layer is the link layer. Here is where information is transferred via a packet. In BLE, there is only one packet format as seen here, built up of a preamble, an address, a data unit, and finally a CRC. The data unit, referred to as a PDU, can be one of 7 advertising PDUs, or only one of 2 data PDUs. The link layer is responsible for coordinating the adaptive frequency hopping as dictated by a master. By keeping the packet complexity and control procedures to a minimum, a very fast connection time of less than 3 milliseconds can be achieved. The link layer can be thought of as a one-hot state machine. Let's take a look at what is going on in each of these states. As would be expected, nothing is really going on in the standby state. No packets are being moved about. In the advertising state, a device will initiate an advertising event somewhere between once every 20 milliseconds all the way up to 10 seconds. A device may advertise as connectable, like a proximity fob, or non-connectable, like a temperature sensor. In scanning mode, a device listens for those advertising packets being sent by a broadcaster. A device in the initiating state is really only listening for packets from a specific device so that a connection can be established for additional communication. And finally, devices in a connection state will be defined as either a master or a slave, and this is where real data transfers happen, or they are known as connection events. Now, consider for a moment states and power usage. As a developer, you must consider trade-offs and define your use cases before accurate power consumption can be determined. Take, for example, a thermometer, a non-connectable device. It can turn itself off while it does not have any data to report. However, a device like a proximity fob, that is a connectable device, may need to wake periodically but may not enter a connected state for days, i.e., your car key in your top drawer while you're on vacation. Now, this leads to a timing issue between the peripheral and the central, advertising and scanning. To save power, the slave does not want to be sending advertising events too often, burning valuable battery power. And the master does not want to be scanning all the time either. Look at the example here with the different rates being used. A master will scan for 11 milliseconds out of every 1.28 seconds. And a slave will advertise only once a second. It may take hours for those 2 cycles to actually cross. So, as a designer, you may need to dynamically adjust the rate at which your master or slave scans or advertises depending on the nature of the data. Here is an example timeline of what happens during an advertising event. A peripheral will send out an advertising packet as often as defined, rolling through the three advertising channels, 37, 38, and 39. A central will be listening for these advertising packets on those channels. Now, a central that wants to continue the conversation will send packets to the advertising peripheral to do one of several things. Perhaps this is to create a new connection, or it could be to reestablish a connection that was lost due to some event, like you walked out of the room and too far away from the central. Now, once a device is moved into the connection state, connection events will occur. Such events can be seen here. This is where data is transferred, as well as many maintenance items are taken care of. Things like feature capabilities, versions can be exchanged, as well as events like a commanded disconnect or a simple ping. In this timeline, we can see on the left where an advertising event establishes a connection. Then, on the right, the connection events take place to communicate data and control over the 37 data channels. Alright, let's move up the stack a bit. Into the logical link control and adaptation protocol, the attribute protocol, and the security manager layers. First off, the L2 cap of Bluetooth Low Energy is very similar to that of standard Bluetooth L2 cap by constraint. Basically, it is in charge of muxing the upper protocols, which I will address shortly, into the link layer. This layer is fairly transparent. Next up, the attribute protocol is based on a server-client model. In short, the server has services with attributes comprised of characteristics, where real data information lives, and the client has use cases, or to be more easily understood, applications, that want the server data. Next, the security manager is a complex little guy. This is where all the pairing and bonding, which I'll explain on the next slide, is taken care of. There are many shared keys with an AES 128-bit counter mode cipher block chaining message authentication code encryption engine running. Whew, man, that's a mouthful. Well, thankfully it's also known as the CCM for short. In addition to the CRC of the link layer, the security manager provides message integrity check, or MIC, for each new packet, which is 32 bits in length. So, for any of us that have played with a Bluetooth device, we're familiar with the term pairing. What does that actually mean, and how does that relate to bonding? Well, when a device is paired, it simply means that a connection is made and basic information is exchanged. Now, to become bonded, the paired devices agree on security capabilities and features to use with which they will establish a trusted relationship. This relationship is then stored on each device for faster future connections. I guess you could say it's like dating versus being married. Alright, up to the next layers. The generic attribute profile and the generic access profile. But before I discuss the GATT and the GAP profiles in detail, a little more background on the upper layers of Bluetooth is useful. Since Bluetooth, in general, is based on an object-oriented model, we need a method to characterize commonly used data structures. Simple things such as counters, rates, and even temperature are examples of these common data structures. This is where the upper layers build upon the server-client attribute protocol we discussed previously. The data we want to collect, like the steps taken, heart rate, or maybe the ambient temperature, will be defined as the characteristics in a profile of a server. So, what is a profile? A Bluetooth profile defines the required functions and features of each lower layer in the stack using attributes. I think the best way to understand a profile and all that is encompassed by one is to use the colorful graphic on the right here. In short, a profile has services, services have characteristics, Characteristics contain values and descriptions of those values. Now, to be able to address each of those above attributes, we need a way to identify them. Thankfully, the Bluetooth SIG employs the use of the UUID, or the Universally Unique Identifier, for this purpose. Now, there are many SIG predefined profiles, services, characteristics, and descriptors that can be seen on the Bluetooth developer's website. Such profiles as blood pressure, heart rate, proximity, running speed are only a few examples of such profiles. Here are a few additional example characteristics and descriptors that have SIG-defined UUIDs that you can use in your application as part of the interoperability effort Bluetooth Low Energy is tasked to achieve. Now keep in mind, you are free to use your own UUIDs as needed. So what? Profiles, services, how does that apply to you? Well, every BLE device is required by the upper layers of the protocol stack to maintain a GATT server database. This is a data structure that must have a GAP service as well as a GATT service declared. These are two fundamental services defined by the SIG. This here is a code snippet from a heart rate monitor profile showing the two required services with characteristics and the UUID fields populated. So, back to the Bluetooth Low Energy protocol stack. The generic access profile and the generic attribute profile. Here are the details of the GAP profile. It is required by the Bluetooth specification and, as I just mentioned, the low energy spec as well. It has two mandatory characteristics along with two optional characteristics and one conditional characteristic. The GATT profile is outlined here. It is required by the BLE spec, but not the generic Bluetooth spec. As you can see, there is only one optional characteristic defined here. Okay, well that was a lot of work to get through just those two upper layers of the protocol stack. The time and effort was not in vain though, as this is where you will spend much of your time in coming to understand how to create custom profiles and services for your custom BLE devices. Now recall that the client side of Bluetooth Smart has use cases like phone applications, websites, things that will be requesting data from a server. The server will need to be running code that can serve up the custom profile service characteristics that will be your secret sauce and your key to success. As an example, here is the GATT database, excluding the GAP and GATT services we looked at earlier for a heart rate monitor BLE device. This device declares two services, the heart rate service and the device info service. Now, looking at the heart rate service, you can see that it has two characteristics and each of those have a descriptor associated with it. The device info service simply has three characteristics declared. Now, as a last step in understanding the BLE stack, let's tear apart one of these services. Here we see the heart rate service and its first characteristic and descriptor. The service has a handle for accessing the structure throughout the code space and the UUID as defined by the SIG in a header file. The first characteristic has its handle and SIG UUID, followed by a property and permissions. These will be covered in more detail in the next IoT workshop. The last entry in the characteristic declaration is where the actual heart rate value will be stored. It has a length of 4 16-bit words and is initialized to 8 million hex. Finally, the descriptor for the above characteristic is declared. Again, it has a handle and UUID, followed by its permissions, and most importantly, the size and initial value of the actual descriptor value. Okay, enough about technology fundamentals, specs, and protocols. Let's bite into some meat here and discuss real Bluetooth Smart devices. Broadcom has several options to fit your needs. First off, I'll detail the Broadcom 2073X family of Bluetooth Smart SoC devices. This is a true system-on-a-chip device that has a processor and peripherals, memories, and an RF section, all accessing a common system interconnect bus. Here are the highlights of the SoC device. It's a 1.2 volt core. The processor is a Cortex M3 microcontroller with its own EEPROM and serial flash interfaces. There are multiple SPI and UART interfaces, as well as an I2C master. In addition to the microcontroller interfaces, there are on-board peripherals such as RAM and ROM, an analog to digital converter, GPIOs, PWMs, even an LDO. The most important part of this SoC is the Bluetooth Low Energy RF radio. The SoC offers a single-mode, single-chip BLE solution. The stack, which we just covered, is incorporated into the SoC along with security features in the ROM. Also included in the ROM are several BLE applications which the device can be configured for. Additional feature capabilities included in the SoC device are key scan, auxiliary clocks, triac control, a quadrature sensor, a touch sensor, and a real-time clock. The SoC can be set into many different low-power modes and may use different oscillators to fit your needs. All of these features are integrated into a single SoC device suitable for high-volume applications. For those of us that won't reach that high volume level, Broadcom offers a module with even more features. These SIP modules, designated by the S at the end of the part number, incorporate the SoC as I just detailed. In addition, they include an RF antenna, a bandpass filter, a crystal, and a 512 kbit EEPROM for application storage. There's also a low-power LDO included that powers the SoC chip, the filter, the crystal, and the memory. It is designed to be powered by a single coin cell battery for long life. Basically, everything you need is in this module. So, what are the advantages of using the module over the chip? Well, they're very small, only 6.5 by 6.5 millimeters square and only 1 millimeter tall. They are Bluetooth Qualification Body Qualified, or BQB, with Tier 1 regulatory limited modular approval. This requires you only need to validate host spurious emissions of your final product. You can use Broadcom's FCC ID and qualify in just a few hours. This is roughly $1,500 to $3,000 based on current lab rates. For example, standalone BQB and regulatory internal and external costs can run upwards of $100,000. This adds $1 per unit to the chip price, assuming 100,000 units. If volume is less than 100,000, the delta is even lower. The BQB and regulatory fees across only 50,000 units per year adds $2 a unit. This doesn't even factor in the time to market advantages and potential problems encountered during BQB and regulatory testing. The integrated module is essentially the same price, but Broadcom does the design, regulatory test, and manages yield. So, here is Broadcom's portfolio of Bluetooth 4.1 capable Bluetooth Smart SoCs and modules. They all have the features I just covered. Each family member builds on the predecessor. We start with the 732, then up to the 736, and the 737. As you can see here, the 36 adds over-the-air updates, wireless charging, and support for the device to be both a master and a slave at the same time, above and beyond what the 32 features are. The 37 has all of that, plus the RSA security algorithms in the ROM, and near-field communication integration, and it can also support audio rates. Now that you have a basic understanding of what Bluetooth Smart is and are now familiar with a few of the modules Broadcom has to offer, how can you take the next step into creating your own Bluetooth Smart device? Mpression's Odyssey Bluetooth Smart Sensor Kit is the perfect way to get started on your design journey. The Odyssey Bluetooth Smart Sensor Kit allows you to create a custom Bluetooth LE device in minutes. It combines sensors for ambient light, UV light, proximity, gesture, pulse rate, temperature, humidity, and acceleration. It is designed with a USB-enabled microcontroller and a Broadcom BCM20737S Bluetooth SMART module for connectivity. Here's a block diagram of the sensor board with the Broadcom module and associated sensors. You can easily expand the board's processing with an Altera Max 10 FPGA add-on board that has Arduino expansion capabilities as well. An Mpression website allows you to create a smartphone app to control your custom Bluetooth device in minutes without writing a single line of code. The app is built upon a framework that allows the user to choose a personality for the BLE device based on the available sensors. Once a personality is selected, the sensors are configured and the FPGA is loaded, if applicable, and the appropriate control app is then loaded onto the smartphone. Register today as a priority customer and get the Mpression Odyssey Bluetooth SMART sensor kit at an introductory price of only $25. Coming up in the next IoT vWorkshop, I will showcase the Broadcom Software Development Kit, also known as the Wicked Smart Environment. In this workshop, I will use the SDK to explore the infrastructure of the applications that can be run on the Broadcom module and how you can modify, compile, download, and debug these applications. Thank you for watching this video workshop, and if you have any questions regarding any of the content you have seen today, feel free to send an email to workshophelp@macnica.com and include IoT1 vWorkshop in the subject line, and one of our Bluetooth Smart experts will promptly reply to your inquiry. I'm Troy Jones, and thank you again for watching, and look for our other IoT and Altera SoC on-demand workshops on the Macnica Americas website.